Welcome to Jeremy's IT Lab. This is a complete course for the CCNP ENCOR, Enterprise Core exam. In this lab, we'll review the various concepts we covered in the previous lecture video about MST regions and what happens when you connect them to each other. I changed the topology a bit from the lecture video. Instead of 2 regions, this LAN has 3 regions. Region 12 with VLANs 1 to 100, Region 34 with VLANs 1 to 150, and Region 56 with VLANs 51 to 150. Let's get started with Step 1, in which we'll do some basic setup. It says to create the necessary VLANs on each switch, configure the links between them as static trunks that allow only the necessary VLANs, explicitly disable DTP, and configure the unused VLAN 999 as the native VLAN. So when it comes to allowing VLANs between regions, we'll allow VLANs 1 to 100 between Region 12 and Region 34, and allow VLANs 51 to 150 between Region 34 and Region 56. Those are the VLANs shared between these different regions, so traffic in those VLANs should be allowed to travel between regions. To speed up the configurations, I've made a notepad to copy and paste the commands. I highly recommend doing this for labs with repetitive configurations on multiple devices. It really speeds things up. So let's look at switch 1 first. We'll configure both G00 and G01, set the trunk encapsulation, static trunk mode, disable DTP, allow VLANs 1 to 100, all of the VLANs in this region, and then set the native VLAN. So I'll copy these commands, and then paste them into the CLI of switch 1. Okay, switch 1 is done. Let's go back to the notebook for switch 2. The only difference here is that switch 2 only has one active interface, so we'll configure only G00. Highlight and copy the commands, and then paste them into the CLI of switch 2. Okay, region 12 is done. Next, let's configure switch 3 and switch 4 in region 34. Switch 3 G00 connects to switch 4 in region 34, so we'll allow all of the region's VLANs, 1 to 150. G01 connects to region 12, so we'll only allow region 12's VLANs, 1 to 100. And then G02 connects to region 56, so we'll allow only VLANs 51 to 150. So let's copy all of these commands, and then paste them into switch 3's CLI. Okay, as for switch 4, it is connected to switch 3 in region 34 and to switch 6 in region 56, but isn't connected to region 12. So let's allow all 150 VLANs on G00 and only region 56's VLANs, 51 to 150, on G01. I'll copy the commands for both interfaces and then paste them into switch 4's CLI. Okay, we're done with region 34. Finally, region 56. The configurations here are simple. On both switch 5 and switch 6, we'll configure both G00 and G01, allowing VLANs 51 to 150. Okay, let's copy the commands and then paste them into the CLI of switch 5, and then into the CLI of switch 6. And we're done with region 56. Now let's move on to step 2, in which we'll configure each MST region. We should configure each switch's priority as shown in the diagram. I've indicated each switch's priority in MSTI 0, MSTI 1, and MSTI 2. And we should configure the region names shown in the diagram. So region 12, region 34, and region 56. And all regions should use revision number 1. And then in each region, we should map the first half of the VLANs to MSTI 1 and the second half to MSTI 2. In region 12, that's 1 to 50 to MSTI 1 and 51 to 100 to MSTI 2. In region 34, that's 1 to 75 to MSTI 1 and 76 to 150 to MSTI 2. And in region 56, it's 51 to 100 to MSTI 1 and 101 to 150 to MSTI 2. So let's configure the switches in order, starting with switch 1. Before any other configurations, let's enable MSTP with spanning tree mode MST. Next, let's configure switch 1's priority in each instance. For MSTI 0 and MSTI 2, switch 1 should have the default priority, 32768 in MSTI 0 and 32770 in MSTI 2, which is 32768 plus 2 for the instance ID. So I'll just configure MSTI 1's priority. Spanning tree MST1, priority 4096. It says 4097 here, but that's including the extended system ID, which is 1. When you configure the priority, it must be in increments of 4096. Okay, now I'll enter MSTP config mode. Spanning tree MST configuration. First set the region's name. Name region 12. Then the revision number. Revision 1. And then VLAN mappings. Instance 1, VLAN 1 to 50. Instance 2, VLAN 51 to 100. And then end to apply the changes. Next, I'll do the same on switch 2. First, enable MSTP with spanning tree mode MST. In switch 2's case, MST1 should have the default priority, but MSTI 0 and 2 should have 4096. I'll configure them both with spanning tree MST 0, 2, priority 4096. Next, MSTP config mode. Spanning tree MST configuration. Set the name and revision with name region 12 and revision 1. Then the same VLAN mappings as switch 1. Instance 1, VLAN 1 to 50. Instance 2, VLAN 51 to 100. And end to apply the changes. Okay, we've only configured these 2 switches. The others are running STP, or rather PVST+, which is the default for these IOSV switches. I'll use show spanning tree MST 0, and notice this line here. Route this switch for the CIST. Currently, switch 2 has the lowest priority of all of these switches, so it has identified itself as the CIST route, the route for the whole LAN. And switch 1 should agree with switch 2. I'll go on switch 1 and use show spanning tree MST 0. Notice the route and regional route. Both have the same MAC address and priority 4096, which is what we configured on switch 2. And look down at switch 1 G01. It says bound PVST. Think back to the definition of a boundary port I gave in the lecture video. A port that connects to a link that belongs to a different region. A link belongs to a region if the link's designated bridge is in that region. In this case, switch 1 is the designated bridge for this link, as shown by G01's designated role. So why is G01 a boundary port? It's because it connects to a non-MSTP switch. In the next video, we'll cover the details of how MSTP interacts with non-MSTP switches, those running PVST+ or Rapid PVST+. But for now, just remember that a port connected to a non-MSTP switch counts as a boundary port, even if this switch is the designated bridge for the segment. Okay, like I said, we'll cover that in the next video. Let's move on with the rest of the configurations for this lab. I'll configure switch 3 in region 34 next. First, enable MSTP with spanning tree mode MST. And configure MSTI1's priority with spanning tree MST1, priority 4096. Then enter MSTP config mode. Spanning tree MST configuration. First, set the region name with name region 34, and the revision number, revision 1. Then the VLAN mappings. I'll assign VLANs 1 to 75 to instance 1 and 76 to 150 to instance 2. Instance 1 VLAN 1 to 75, and then instance 2 VLAN 76 to 150, and end to apply the changes. And then switch 4. First, enable MSTP with spanning tree mode MST. Then configure switch 4's priority in MSTI 0 and MSTI 2 with spanning tree MST 0, 2, priority 4096. And then enter MSTP config mode, spanning tree MST configuration, and then configure the same settings as on switch 3. Name region 34, revision 1, instance 1 VLAN 1 to 75, instance 2 VLAN 76 to 150, and end to apply the configs. Okay, let's configure switch 5 and switch 6 in region 56 to finish up this step. On switch 5 first, I'll enable MSTP with spanning tree mode MST. Switch 5 should have priority 0 in MSTI 0 and 4096 in MSTI 1. So spanning tree MST 0, priority 0, spanning tree MST1, priority 4096, and then enter MSTP config mode. Spanning tree MST configuration, configure the name and revision, name region 56, revision 1, and then the VLAN mappings. Instance 1, VLAN 51 to 100, instance 2, VLAN 101 to 150, and end to apply the changes. Finally, I'll configure switch 6. Enable MSTP with spanning tree mode MST, then set the priority for MSTI2. Spanning tree MST2, priority 4096. And then configure the region settings. Spanning tree MST configuration, name region 56, revision 1, instance 1 VLAN 51 to 100, instance 2 VLAN 101 to 150. End. Okay, we're done with all of the configurations. The only new commands we used compared to the previous lab are the name and revision commands to configure the region's name and revision number. Next, we'll move on to step 3, which is really the main section of this lab. Step 3 says to verify the topology, asking quite a few questions that we'll answer one by one. The first question is which switch is the CIST root? If you remember what we covered in the lecture video, you should be able to answer this without checking the CLI. First, what is the CIST? Well, each of these regions runs its own IST, internal spanning tree. So there are 3 ISTs. This connection between switch 1 and switch 2, this connection between switch 3 and switch 4, and this connection between switch 5 and switch 6. The CST, common spanning tree, is what connects the different regions. So this connection between regions 12 and 34, and these connections between regions 34 and 56. Then CIST, the common and internal spanning tree, is the spanning tree that includes both the CST and all of the ISTs, the whole LAN. And the CIST root bridge is the switch in the CIST with the lowest STP bridge ID. That is switch 5, because it has the lowest priority in MSTI 0. To confirm, I'll go to the CLI of switch 5 and verify with show spanning tree MST 0. Next to root, it says this switch for the CIST. So, as expected, switch 5 is the CIST root because it has a priority of 0 in MST instance 0. Now let's go back to the lab guide for the second question, which asks, which switch functions as the CIST regional root of each region? So what is the CIST regional root? It's the switch that represents the region in the CIST. As I mentioned in the lecture video, each region appears as a single logical switch from the perspective of other switches. So, for example, when switches 5 and 6 in region 56 send BPDUs to switches 3 and 4, those BPDUs contain the information of the CIST regional root. In region 56, that is switch 5, because it's the root of the entire CIST. The CIST root is the CIST regional root of its own region. So when switch 5 sends BPDUs to switch 3, those BPDUs include switch 5's bridge ID. And when switch 6 sends BPDUs to switch 4, those BPDUs also include switch 5's bridge ID, not switch 6's. We'll confirm that later. So how about region 34? Which switch is the CIST regional root? Well, the CIST regional root is the switch with the lowest external root path cost through a boundary port. Switch 3 and switch 4 should each have the same cost, 20,000, since they both have a direct connection to region 56. So what is the tiebreaker? It's bridge ID. And because switch 4 has a priority of 4096 in MSTI 0, whereas switch 3 has a priority of 32768, switch 4 should be the regional root. Let's check in the CLI of switch 4. I'll use show spanning tree MST 0. And here it says regional root this switch. So switch 4 is indeed the regional root of region 34. Now it's interesting to note that switch 4 was selected even though it isn't directly connected to the CIST root, switch 5, whereas switch 3 is directly connected to switch 5. That's because the internal root path cost, the cost from switch 6 to switch 5, isn't taken into account. From the perspective of switch 3 and switch 4, they both have the same root cost. Finally, what's the CIST regional root of region 12? Well, only switch 1 has a boundary port, this connection to switch 3, so it should be the regional root. Although switch 2 has a lower bridge ID in MSTI 0 than switch 1, switch 2 has no boundary ports, so it isn't a candidate to become the CIST regional root. Let me just check on switch 1 with show spanning tree MST 0. As expected, it says regional root this switch. Okay, let's go back to the lab guide for question 3. It asks, which switch functions as the IST root of each region? After answering question 2, we can answer this one without looking at the CLI. Each region's CIST regional root functions as the IST root of the region. So as we just confirmed, switch 1 is the CIST regional root of region 12, so it is also the root bridge of the region's IST. And then for region 34, because switch 4 is the CIST regional root, it is also the IST root of the region. Let's confirm that by opening the CLI of switch 3 and using show spanning tree MST 0. So first look at the root information. It has a priority of 0, which is switch 5. So switch 3 recognizes switch 5 in region 56 as the CIST root. However, switch 3's root port isn't G02, which is directly connected to region 56. Instead, it's G00, which is directly connected to switch 4, the regional root and IST root of switch 3's region. So to repeat that, even though switch 3 is directly connected to the CIST root, switch 3's root port in MSTI 0 isn't the port closest to the CIST root. It's the port closest to the CIST regional root, switch 4. As CIST regional root, switch 4 represents region 34 to the outside world, and switch 3 just has to ensure that it has a viable path to reach switch 4. Okay, sorry for being repetitive, but it's important to grasp these concepts, and people often confuse them. Anyway, we covered regions 12 and 34, and for region 56, the IST root is, of course, switch 5. The CIST root is the CIST regional root, and therefore also the IST root of its region. Now let's look at question 4. It asks, which ports are boundary ports? Remember the definition of a boundary port. It's a port that connects to a link that is in a different region. So not all ports connected to another region will necessarily be boundary ports. Let's check switch 1 first. I'll use show spanning tree MST 0. Switch 1's G01 port, connected to switch 3 in region 34, is a boundary port. That's because switch 1 isn't the designated bridge for this link, for the segment between switch 1 and switch 3. Switch 1 G01 is a root port, providing region 12's path toward the CIST root. And if switch 1 G01 is a root port, switch 3 G01 must be a designated port. Switch 3 is the designated bridge for the segment. So I'll go on switch 3 and check. Switch 3 G01 shouldn't be a boundary port. Use show spanning tree MST 0. And as expected, because switch 3 is the designated bridge for the link connecting to switch 1, G01 isn't a boundary port. However, switch 3 G02 is a boundary port. It's an alternate port, receiving BPDUs from switch 5, which is the designated bridge for the segment. Let's go on switch 5 and look at show spanning tree MST 0. Indeed, switch 5 G01 isn't a boundary port, because it's the designated bridge for the link. The link is considered part of its own region, region 56. And the same should be true for the link between switch 4 and switch 6. On switch 4, let's take a look at show spanning tree MST 0. Switch 4 G01 is a boundary port, a root port that receives BPDUs from switch 6 G01, and is therefore a boundary port. This link is part of another region, region 56. And I'll use the same command on switch 6, show spanning tree MST 0, to double check that G01 is indeed a designated port, so it isn't a boundary port. A designated port can't be a boundary port, because if it's designated, it means the switch is the designated bridge for the link. As a side note, you'll find many explanations online that say any port connecting to another region is a boundary port. That definition makes sense, but the 802.1q 2022 standard, the current definition of MSTP, is the one I'm using. And as you can see, the Cisco switches don't identify these ports as boundary ports. Okay, that's enough about boundary ports. Let's go back to the lab guide for step 5, asking what the topology of the CST is, and which ports are forwarding and discarding. Well, we just saw the topology when checking which ports are boundary ports. Switch 1 G01 is a root port in the forwarding state, providing region 12's path to the CIST route. And switch 3 G01, the other side of the link, is a designated port in the forwarding state. Its G02 port, however, is an alternate port in the discarding state. That's because switch 4 is the region's CIST regional route, so the region's root port is on switch 4, and that's switch 4 G01. Finally, switch 5 and switch 6 G01 are both designated ports in the forwarding state. Since region 56 is the root of the CST, both of these ports are designated. Next, let's move on to question 6, which asks each switch's external and internal route path cost. The external route path cost is the switch's cost to the CIST route via the CST, not counting the cost within a particular region. So, for example, switch 5 and switch 6 should both have an external route path cost of 0. Switch 5 is the CIST route, and switch 6 is in the same region, so both have no external path cost. Just to be sure, let's check on switch 6. In the same output of show spanning tree MST0, in the root section, you can see path cost 0. This is switch 6's external route path cost, and as expected, it's 0. And while we're here, let's check its internal route path cost. As a reminder, that's the switch's cost to reach the CIST regional route of its region. So it's switch 6's cost to reach switch 5 within region 56. And it says here, internal cost 20,000, because switch 6 is directly connected. Switch 5's internal route path cost is 0, of course, since it is the regional route. Okay, now let's move on to region 34. This region is one CST hop away from region 56, so both switch 3 and switch 4 should have a cost of 20,000. Let's check the same output as before on switch 3. And indeed, it is 20,000. Switch 3 also has an internal route path cost of 20,000, because switch 4 is the CIST regional route of the region. And let's look on switch 4. It has an external route path cost of 20,000, but no internal cost is shown because it's the regional route. And finally, let's check region 12. It's 2 CST hops away from region 56, so switch 1 and switch 2 should have an external route path cost of 40,000. I'll check on switch 1 first. And as you can see, its external path cost is 40,000. Being the CIST regional route of the region, it has no internal path cost, but let's check on switch 2. In the output of show spanning tree MST0, you can see the external route path cost of 40,000 and the internal route path cost of 20,000. Okay, enough about costs. Let's return to the lab guide for question 7, which asks which ports are master ports and why. So master port is a new port role in MSTP that facilitates connectivity between MSTIs in different regions. The rule we covered in the lecture is that the CIST regional route's CIST route port is the master port for all MSTIs. Switch 5 is a CIST regional route, but it's also the route bridge for the entire CIST, so it has no route port. Switch 1 and switch 4 are both CIST regional routes, and in both cases, G01 is the route port. Let's go back to the CLI of switch 1. In the same output as before, you can see that G01 is indeed a route port. But what if I do show spanning tree MST1? In this instance, it's a master port. Why can't it just be a route port like in MSTI 0? Well, in MSTI 1, switch 1 is the route bridge, and the route bridge can't have any route ports. And it can't be designated because it's connected to a designated port, switch 3 G01. There must be exactly one designated port per link. There can't be two. Instead, the master port role is used to function as a forwarding port that is neither route nor designated. And let's check MSTI2 with show spanning tree MST2. Again, G01's role is master. In this instance, switch 2 is the root, and G00 is switch 1's root port. Again, the master role allows G01 to be in the forwarding state without being a root or designated port. Okay, there should be one more master port in this network, and that is switch 4 G01, because switch 4 is the CIST regional root of region 34. On switch 4, I'll use show spanning tree MST1. As expected, G01 is a master port, and it should be the same in MSTI2, show spanning tree MST2. Okay, it's a master port in this instance too. Okay, to summarize master ports, the CIST regional root's root port is a master port for all MSTIs, except MSTI0, of course. Like root and designated ports, it is stable in the forwarding state. But unlike a root port, it doesn't lead toward the MSTI's root bridge. And unlike a designated port, it doesn't send BPDUs. Finally, let's go back to the lab guide for step 4, which says to examine the BPDUs sent between regions and see what information is included. So you should check the BPDUs sent from switch 6 to switch 4, the BPDUs sent from switch 5 to switch 3, and the BPDUs sent from switch 3 to switch 1. I've included captures in the lab files, so you can look at mine if you don't have access to an actual lab. Let's take a look at the BPDUs switch 6 sends to switch 4. Click on any of the BPDUs, they're all the same, and then open up the spanning tree protocol section. I'll just point out a few things. First, look at the root identifier. The priority is 0, and this MAC address is switch 5's. This is switch 5's bridge ID, because it's the CIST root. And then the bridge identifier. Once again, this is switch 5's bridge ID. In regular STP and rapid STP, the bridge identifier field always indicates the switch sending the BPDUs. This BPDU was sent by switch 6, but it uses switch 5's bridge ID. That's because switch 5 is the CIST regional root of the region, and it represents region 56 in the CIST. So any BPDUs sent to other regions, even those sent by switch 6, are sent using switch 5's bridge ID. Next, notice the root path cost is 0. Switch 6 has an internal path cost of 20,000, but this is its external cost, which is 0. Okay, I'll open up the MST extension at the bottom. The first 4 fields here are the MC ID, MST config ID. And then notice below that switch 6 indicates its CIST internal root path cost. When switch 3 and switch 4 receive BPDUs from switch 5 and switch 6, they look at the external root path cost of 0 that was indicated above to make their decisions about the topology. But switch 6 does indicate its internal root path cost here. Let me quickly open up the switch 5 to switch 3 packet capture. Expand the spanning tree and MST extension sections, and look at the internal root path cost. Switch 5's BPDUs show an internal cost of 0. Let's look back at the network once more. So switch 5 sends BPDUs to switch 3 and advertises an external cost of 0 and internal cost of 0. Switch 6 sends BPDUs to switch 4 and advertises an external cost of 0, but an internal cost of 20,000. You might think that makes switch 5's BPDUs superior, which would make switch 3 the CIST regional root instead of switch 4. But that isn't the case. Switch 3 and switch 4 don't look at the internal cost in the BPDUs. They only consider the external cost of 0, which is tied between switch 5 and switch 6. Then the tiebreaker is bridge ID, and switch 4's is lower, so it becomes the regional root. Okay, just wanted to clarify that. The internal root path cost is included in BPDUs, but when deciding which switch becomes the CIST regional root, they only consider the external cost. Okay, finally, I'll open up the switch 3 to switch 1 packet capture. Click on any BPDU, expand the spanning tree protocol section, and I just want to point out 2 things. First, notice the root path cost is 20,000. That's the external root path cost from region 34, 1 hop away from region 56. And then look at the bridge ID. Which switch's bridge ID is this? Switch 3 sent this BPDU, but like in the previous example, this isn't switch 3's bridge ID. It's switch 4's, because switch 4 is the CIST regional route of region 34. Okay, that's all we'll look at in this lab. This video is longer than most labs we've done, and I spent a lot of time rambling about different MSTP topics. But hopefully this lab and video clarified these concepts for you. That's all for this video. Thanks for watching. Before finishing this video, let me thank my JCNP level channel members who support me through YouTube channel membership. To become a member, please click the join button under the video. Thanks to Jonathan Makura, Velva Jacob, George, Nasir Chowdhury, Gustavo Macedo, Marcel Lord, Dragos Hernea, Zakib Shah, Mayor Salman, Vitaus194, Mark Jackson, Bold1C1U, Gerald Guillaume, Fristas1207, Hector Hernandez, Arpad Conives, 5 Feet, Owad, Daniel Brown, Jose Alvarez, Hussein Yavuz, Samuel Tavares, Kevin Hayes, Roger Bratseth, Brian Grant, Georgi Gemajev, Cats for Life, Adelson Pereira, Farad69, Madmark 50484, Alexandru Stratan, Hiago Bicalho, Lucian Stoichitoyu, DMJ2, Kurt Nell, Dear Diso, Steve Cox, Jasper Yim, Pedro Hartman, Tricky Mickey 123456, Ivano Capuano, Jefferson Steelflex, Toxic, Wilmo Romero, Sinan Sarisinar, Gio, Daniel Andrade, Mike Crumby, Dragos George, Jairo Francisco, Filip Jovanovic, Mateusz Zashinsky, Ruben Hernandez, Electro Jedi, Trevor Goldman, Gavin Paul Tech, Sunny Idigu, Jeffrey C., Chitsinde, Stephen White, Edificare, Fio Fiohain, Dimitro Lis, Faris Al-Zaharani, Jean-Marcel Belmont, Mikhail Chapsky, Hemanth Jabalpuri, Darius D., Juan Morales, Gonzalo Nicolas, Doomed Soul, Christine Schubert, Julio Maya, Josie, Egraso, Komlan Kapedimi, Gokhan Doimaz, Hashem Rodef, Anand Abyankar, JFlow99, Clyde Makorobindo, Adekola Ismail Salami, Orlando Flores, Ray Enriquez, Adrian Martinez, MD Danielwitz, Gabriel Afolabi, GG7, and Rohan Surti. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.